In this presentation, we're going to be talking about the linear regression model fit. And basically what it's going to do, what we're going to do is we're going to talk about this R-squared value, which basically tells us how good our model is at actually fitting the data. So typically, we want to know how well the regression equation, so that linear equation that we developed in our last presentation, we want to know how well it matches the relationship of x and y values that we actually see in the data. And we do this by calculating the R-squared value, which actually has its own name. It's called the coefficient of determination. So R-squared is equal to the coefficient of determination. And essentially it is, something that ranges from 0 to 1 that we ultimately express as a percentage of good model fit. So something that, let's say, is 90 to 99% is a good model. Something that's lower, maybe closer to 0, so let's say maybe 0 to 5%, is a pretty poor model. And so basically this R-squared value is just giving us an idea of, is that linear equation that we've developed, is it a good fit of the data? And as engineers, if our model is bad, then it basically tells us we need to go back and we need to start looking at our data and start thinking about ways in which we can make our model better so that we can make predictions for future data. So you've probably seen this value before, this R-squared value, and typically it's something that you can just easily, it's a box you mark in Excel and it will just display the R-squared value. And we'll do that in a second. But I want to show you that there are actual equations that lead to this calculation. So in order to compute R-squared, we have 4 equations. The first one is EI is equal to YI minus Y1 hat. And this is our residual, so our error. This Y value is the actual Y value of the data, so that exists for the data. And then this Y hat, remember, is our predicted Y value, so based off of our model. So essentially this value we get by using our equation, which states that Y hat is equal to beta 1 xi plus beta naught. So the next equation we have to use to ultimately calculate R-squared is SS sub E, which is the sum of residuals squared. And that equation basically says that we sum our samples residuals. So we take all of this residual, this error, and we sum it up. And then what we do is we go and we calculate the total sum of squares, which essentially is kind of like a computation of the variance. Where what we're doing is we're actually going in and we're computing, what is that difference, that different distance between the actual data point and the average data point that we see specifically within the data for all of our data points. And so using these 3 equations together, because you can see how this sort of plugs in nicely here, we get an equation for R-squared equal to 1 minus the sum of squared errors minus the sum of total squares. So if you want to go in and take your data set, what you can do is you can actually go in and calculate, your y hat, and then go in and calculate all of your errors for each point, and using that point, your error points, you can sum them up here, and then you can also go in and you can actually compute your yi value, or your difference between your yi, so your specific data point, and the average for your data set. Square that, and then you can actually go in and calculate r squared. But as you can see, it's kind of a pain in the butt, because if you have a lot of data, then you're calculating a lot of residuals, and then you have to go in and you have to sum you have to sum the squares of those residuals before you can even go in and calculate r squared. So let's actually go into Excel, and I'll show you the quick and easy way to do it, because at the end of the day, as an engineer, you're never going to sit down and do hand calculations. You're only going to be doing things in Excel to make your life as easy as possible, because time is money. So the first thing that we can do, now that we're here, if we want to, is we can actually go in and do sort of the easy, quick and dirty way to get our r squared value. So again, you're going to right click on your data, hit add or click add trend line, and then down at the bottom you can click display r squared value on chart. And so just like that, we have an r squared value of 0.804, which basically tells us that the line that we have is about an 80% fit of the actual data. So our model is, about 80% accurate, which is, okay. In engineering, we're typically shooting closer to 99%. This is where your, if you've ever heard of things like Six Sigma come in, that means that, it's 0.99998 or something, but it's basically saying that the models that they're using are so good that it's almost perfect. But let's go in and actually show you how to calculate this r squared value, and to do that we have some quick and dirty method, and the first thing is to figure out what those residuals are. So to do that, let's type in residuals. Obviously I am an engineer and can't spell. And our residuals are equal to y1, so in our case the cost, minus our y hat value, and to get to y hat, remember it's beta 1 times x sub I plus beta naught. So in our case, it's 0.1034, and I'm going to put these in parentheses. Okay, I know. Times x sub I plus beta naught. Just click on this, and because I want this just to be a value that doesn't change, and then I'm going to add a couple more parentheses because I'm anal, and there you go. And we just drag and drop, and eventually we get some residuals here. So now I can go in and I can calculate my sum of squared errors, and to do that, it's equal to, in our case, we can use the sum product command. And what we do is we actually double click this, and we get sum squared errors equal to that value. And then the last thing we do is we put the sum of, or the total sum of squares, and to do that, it's just equal to y1. So to do that, we're actually going to use the var command again, so that variance command, because the equation is the variance times n minus 1. So it's similar to what we used for the denominator up here. And so it's for our y values, and then we're going to multiply it by 11 because that's n minus 1. And then we get the total sum of squares to be this value, and so then our r squared value is just equal to 1 minus the sum of squared errors divided by the total sum of squares. And voila, you see that we get an r squared value of 0.804. Thanks.